In this video, I'd like to continue our discussion on Unit 3, Part 2, Lesson 2. I've added a couple pieces to our notes already, so you might want to take the time to do so as well. First off, as a reminder of the general form of an exponential growth function, and I've also added 8 empty axes here for us to sketch a graph. Now, it is also important to note that while all 8 of these examples are written with a base value of 6, any A value here would suffice. Any A value in this position would be okay, as long as A is positive and A is not equal to 1. Those are the 2 restrictions that we have on the base values for exponentials. So let's talk a little bit about the behavior of each of these functions. Part A, well, we've got a base that's being raised to some exponent. Now, as that exponent, which is the variable, increases, then the result of this calculation also increases. If we decrease the value of x, even towards negative numbers, because we can have negative exponents, the numbers will get smaller. There is no b value to indicate any other horizontal asymptote. We saw that in the temperature problem from last video. This b value, which represented ambient temperature, that just created a horizontal asymptote for us to approach. This was our b value. We don't have that here, so with no b value, our horizontal asymptote will exist at 0. So if we imagine this horizontal asymptote at 0 and a function that will increase from left to right, then I think this would be a pretty decent sketch. It's also worth noting that if x were 0, the math would be pretty easy to create a checkpoint. When x is 0, 6 to the 0 power is equal to 1. So when x is 0, y is 1, this coordinate 0, 1 is going to be on that graph. We know that the equation has to run through it. And one more note about this growth factor. Since the growth rate is 6, then for every horizontal step to the right, we would actually grow 6 times as tall. Now, this sketch obviously is either not drawn to scale or has a different y-axis scale than x-axis scale, but it is worth noting that every one horizontal step to the right will produce a new data point that's 6 times as tall. It's not just 6 units taller, but it's 6 times as tall since our base value is 6. Regardless of what the base is, that's our multiplier. That's our growth factor for each horizontal step. For part B, it might be worth noting that 6 to the negative x power, well, since that's got a negative exponent, that would be the same as 1 over 6 to the positive x power. Now here again, a test point of 0 might suffice. If I substitute 0 in for x, then I get 6 to the 0 power, which is 1. This 1 divided by the denominator's 1 is also 1. So when x is 0, y is equal to 1, we again have this same data point. But what's going to happen if we start substituting larger and larger values for x? Well, again, this component, 6 to the x power, will get larger and larger, but when a large number when a number 1 is being divided by a large number and gets progressively larger, then our calculated result tends towards 0. So this thing's leveling off towards 0. And that's also supported by the notion that there is no b value that's being added on the outside. With no b value written, we can assume that that value is 0. And so we're tending towards 0 again. We have a horizontal asymptote at 0, and the graph, instead of racing up towards infinity, is racing down from infinity as we move from left to right, and we're leveling off towards 0. For part C, we have the same function as part A, only this time there's a negative sign in front of it. And do you recall what happens if we apply a negative sign in front of an entire equation? This would have been discussed in a transformations unit, either in geometry or algebra 2. Well, we take the original function, and I'm just going to real lightly sketch it here. And when we have a negative symbol in front of the original function, it reflects that image over the x-axis. So in this particular case, this is the sketch that we're after here. It doesn't have to be perfect, but the general shape is what we're looking for. This is still considered a growth function. It's not considered a decay function. Even though the y values are decreasing, they're going down. When we talk about growth versus decay, we're really discussing the distance from that asymptote, in this case y equals 0. So this distance is getting bigger and bigger and bigger, so we would still call this a growth function. The negative symbol, whoops, this should have been 6 to the power of x. This negative symbol simply reflects over the the x-axis. So same thing happens with part D. We had the same equation as part B, 6 to the negative x power, only a negative symbol in front of it. So that too should be flipped over the y-axis. And this particular example might be considered a decay function because the distance between the horizontal asymptote is getting smaller and smaller as we move from left to right. Now, while we're walking through this, I know I'm adding a few comments and sometimes I'm rewriting the functions. I personally think that this would be a good idea to create a set of flashcards with this data. And maybe instead of using the number 6, you can change that number 6 to the letter A. And that way we can more generalize this rule. And on one side of the note card, you can write the function as it's given to you in part A through H, right? Make one side of the note card made up of just these functions here. And then the other side of the note card, you can have the sketches of these graphs drawn. And that'll help you better understand or perhaps even memorize the behavior of these functions so that we can reference them at another time. With part E, this equation is very similar to part A. We have 6 to the x power, only this time we do have an offset for the b value. So if we've got y equals 6 to the x power, we know that this would be a function that races off towards infinity, that has a horizontal asymptote at y equals 0. But because of the negative 1, we're actually going to shift this down 1 unit. And we can envision that if we use the number 0 again as a checkpoint. 6 to the 0 power is 1. 1 minus 1 is 0, so the data point 0, 0 is going to be on the graph. And this exponential growth function has to run through that point and race upward towards infinity as it did before. As we increase this x value to a larger and larger number, 6 to that power will be larger and larger in and of itself. For part F, we have 6 to the x power minus 1. Let's just create a checkpoint real quick here, because hopefully you've noticed with the first 5 graphs that all of the shapes are the same, just the orientation is slightly different. So in part F, we've got 6 to the 0 power minus 1. Well, 0 minus 1 is negative 1. And 6 to the negative first power, 6 to the negative first power is the same as 1 divided by 6 to the first power, or just 1/6. So this tells us that when x is 0, we get a y value of 1/6. And that's probably not all that helpful. But let's imagine for a second that we use the number 2 in place of x. We use the number 2 in place of x instead of 0 this time. Well, now we've got 6 to the first power, which equals 6. Now we've got another data point. So when x is 2, we've got a y value of 6. Again, my y scale can be off just a little bit. And now we're starting to see the trend here. We can certainly fill in the sketch with these 2 data points, but let's just create one more to be safe. Let's use an x value of 1. 6 to the first power minus 1 is equal to 6 to the power of 0, which equals 1 in and of itself. So when x is 1, we get a y value of 1 as well. And now we can really clearly see this exponential curve And in general, it follows the shape that we saw before. But what's interesting is that this graph, and I know it's a little bit off because of the data points I tried to plot here, but this graph is identical to part A, except it's been shifted over to the right 1 unit. So part A struck the x-axis or the y-axis at 0, 1. For graph F here, it essentially struck this imaginary vertical axis 1 unit to the right, but every other data point would have been exactly the same. So this subtraction of 1 inside the grouping symbol surrounding the x, all that does is it provides a rightward movement. And so I keep referencing this notion of transformation of functions. And this might be a topic that you want to look up on your own so that you can become more comfortable with it if it's not already familiar to you. But transformation of functions will allow you to take a parent function, you may even want to search that phrase too, a parent function, and shift or stretch or translate it into new positions. And that's essentially what we're doing here. We're starting with a parent function or the basic function of exponentials, and we're moving it to different positions. For part G, I think it might be more helpful to write it this way. For part G, let's say that y is equal to 6 to the negative x plus 1 power. This way we have the same function as we had in part B. In part B we had y equals 6 to the negative x, and part G we also have 6 to the negative x. But surrounding that, and we should recognize the general shape of this being a decay example. Now if it would help, let's go ahead and use some test points here. If x were 0, when x is 0, we have 6 to the 0 plus 1, or 6 to the first power, which is 6. So we've got this data point that's pretty high in the air relative to the others. When x is 1, well, that's kind of interesting. When x is 1, we get negative 1 plus 1, which is 0, and 6 to the power of 0 is also just 1. And if we were to use another x value like 2, again, the math becomes a little bit more clear. Negative 2 plus 1 is negative 1. 6 to the negative first power is 1/6. So at an x value of 2, we're tailing off, we're dropping off towards our horizontal asymptote and leveling off at y equals 0. And you may be asking yourself, well, in part F, we had a rightward shift when the number 1 was subtracted from the x group. And I thought the rightward shift is always the opposite of this symbol here. And you are correct. There is a rightward shift to this graph. We did slide it to the right, but there is a problem or an apparent violation here because of the plus symbol. Normally that means a leftward movement. But the one thing you've got to remember is with these transformations is the x has to be isolated and solo. We can't have this negative symbol in front of it. So one way to clarify that confusion or clarify that argument is to write this expression this way. If we factor a negative 1 from x, we would have the negative symbol that indicated our decay outside of a grouping symbol, and now when we factor that negative sign from negative x, we get positive x, take away 1. And here's this subtraction of 1 that indicates our rightward movement, our rightward shift, and this negative symbol here also predicts or previews the decay of this particular equation. Now lastly, part H. I'll again rewrite this because it's not quite in the same format that we saw before. Let's call this y equals negative 6 to the x power plus 1. And now you'll recognize that negative 6 to the x power, well, we saw that back here in part C. So the general shape of the graph matches part C. And we also have a b value that offsets this graph. So rather than leveling off or tending towards 0, it's going to level off, tend towards 1. And because of the shape in part C being an exponential growth, but running downward and away from the horizontal asymptote, then I think a good sketch for this graph, of course, would look like this. Now here again, the discussion in this video is not meant to be, not meant for you to create perfect graphs that are drawn to scale, but to generally recognize the behavior and the shape of the functions. One thing that I find particularly helpful when trying to graph these, if the index cards aren't working for you, or if Quizlet online isn't working for you, then it might be worthwhile just to open up a graphing calculator and start entering some of these examples. In this particular case, I drew the equation 6 to the 1 minus x power here on the graph. And if you're using the TI Inspire, you can press the Tab key and you can enter another expression. And this last example was 1 minus 6 to the x power. And it creates the graph for us as well. And so I think it's a good exercise to start typing your expression here and predict what the shape would look like. And then when you tap enter, you'll be able to see the shape on the screen. And for the most part, a scale centered at the origin, standard size, should be sufficient for us to see the behavior of the graph. Now I will admit, though, in part H here, there was a bit of a discrepancy in what we saw on the graph. Well, I think the data points are pretty much okay, but based on the scale that the calculator provided, it doesn't quite look the same as what we sketched right here. But again, the general shape is correct. It's a exponential growth function that's running downward and away from the horizontal asymptote. So I would be okay with that sketch for part H. It doesn't quite have to be as precise as what the calculator created. I think we'll go ahead and skip this equation for right now. You'll see some of those in Math Excel, and you'll be able to practice with them since we've seen them before. I'd rather finish up the last few minutes of this video talking about this particular example. What if we had a bunch of data points? Could we find the exponential function that fits those data points? I think we should be able to, and let me give you a couple hints along the way here. First off, we have a horizontal asymptote at y equals 0. So since y equals 0, when we think of our general form, c times a to the x power plus b, or as I prefer it, f of x equals c times a to the x power plus b. Well, since there is a horizontal asymptote but it exists at 0, we know that this 0 also represents b, and we can essentially drop that from our general form. Now the other thing that I want to point out is that we often use a test point on the y-axis. We like using x values of 0, and if the y value for that is provided for us, then we've got a pretty good start for this particular type of problem. In fact, I used this technique back in the word problems in the last video. We can determine our growth factor with this coordinate, and we can also determine our initial value. I think we'll go after the initial value first. We know that f of 0 is equal to c times a to the power of 0. And we also know that f of 0 is equal to 1. The f of 0 represents the y-coordinate when x was equal to 0. So if 1 is equal to c times a to the 0 power, and we know that a to the power of 0 is also equal to just the number 1, then c in and of itself is equal to 1. And that's a good start. We now know that c is equal to 1. If I pick any other data point, this, or even this one, I can now find the growth factor. Let me show you how. Let's pick this first one here. When x is 1, the y value becomes 3. We also know that c is equal to 1, so we now have 1 times a to the first power. Well, f of 1 is the y value when x is 1, and that ended up being 3. 1 times a to the first power, well, that's just a, and we now know that a is equal to 3. But even if we had used this test point here, that would have been okay. F of 2 is equal to 1 times a squared. and f of 2 was equal to 9. 9 is equal to a squared, therefore a is equal to 3 or negative 3, using our math. We would throw out negative 3 because we can't have an a value of negative 3. This a value must always be positive and not equal to 1. So we would have thrown that out and again obtained an a value of 3. And I think that's it. We now have the form of the equation that we're after. F of x is equal to 1 times a, oops, the a value is 3, 1 times 3 to the x power, or f of x equals 3 to the x power, or even different still, y equals 3 to the x power. And again, we were able to establish this rule by simply looking at 2 data points. So I hope this video helps. If you have further questions, please let me know. Thanks for watching.